Many SRD systems make effective use of FPGA for data acquisition and heavy lifting DSP processing. FPGAs are by nature reconfigurable, but SDR systems often fail in exploiting this interesting opportunity at runtime. Some attempts to overcome this limitation do exist, and the best known is clearly the RFNOC framework. In this presentation, we show how it is possible to make effective use of partial reconfiguration capabilities of modern FPGA devices. Extending the range of applications RFNOC can be applied to. Unfortunately, support for PR is not yet available in the software stack of commercially available SDR devices. The objective of this work is encouraging its integration. Please welcome Anthony Convers.
Hello everyone. I will present you FPGA partial reconfiguration in software-defined radio devices. I am Anthony Convers. I have 10 years experience in hardware development. Previously, I worked in multimedia group at EPFL, and since six years, I was working at Reconfiguration at HEGVD in Yverdon-les-Bains in Switzerland. So our plan for the presentation is a brief introduction and an overview of RFNOC. I will explain you also partial reconfiguration, and I will continue with partial reconfiguration on the SDR platform. I will describe our modification on the design to apply the partial reconfiguration, and I will show you our testing. I will have a short demonstration, and finally we can conclude with the conclusion on the future works. So, this work was partially funded by the European Space Agency inside the SDR Makerspace initiative. So, the goal of SDR Makerspace is to develop a variety of activity around communication and SDR. So if I give you an example, so we can write a service on a small satellite. So in this satellite, we can have many services running, and we would like to reprogram one activity by our program. So we arrive to the activity SDR FPGA with partial reconfiguration. So the objective was to develop a proof of concept of partial reconfiguration in SDR platform. So I will have a short introduction of what is an FPGA. So it's a field programmable gate array. So it's an array of programmable logical blocks. So the user can write a program in HDL languages to configure the FPGA. And the FPGA, when you program it, it is fixed with the configuration you loaded. And the FPGA is high computational power, so you can run in parallel many operations, but the development is difficult and time consuming, and it is better to be an expert in the domain to have a good result. And so we arrive to the SDR devices. So most of them have an FPGA. So it is often in between the RF module and the processor, and the FPGA can run some signal processing operation. And the GNU Radio framework simplifies the development of the signal processing application. So with this framework, you can have different functionality, and we can choose which operation could be run on the processor or run some part on FPGA, or you can run all the design in the processor, it is what you want. You can decide if you want to accelerate one functionality to use this functionality on the FPGA. But to have the functionality on the FPGA, you need to use an RFNOC block. So that's why the open source framework for FPGA of ITUS research in the SDR devices are created, and it's called RFNOC. So this simplifies the development of the signal processing algorithm in an FPGA. So RFNOC will give you a library of blocks which many operations. So you can have FFT, FIR, gain, many blocks like this. And you can use it in the glue radio flow graph. So you can take a block, an RFNOC block, add it in the glue radio flow graph, and after you can run the graph, and the graph will collect the data directly from the FPGA. So as you can see here, we can have some RFNOC block like the radio and the FFT, and all are in the FPGA size, and it is communicating with the host to to collect the data, and after you can use it or display the data, whatever you want. So if you go in more detail in the internal structure of an RFNOC block, so it uses a NOC shell access stream interface. So and it expects to have a CHDR packet, and all of the RFNOC block is connected via a crossbar, so we can see it here. So all the RFNOC blocks have the same command interface, and all the blocks have an ID. So we can recognize the block with his ID. So when we want to construct a design, we need to create a combination of the different blocks we want to use, and to implement this in the FPGA. That's why for our test we have used the E310 platform from ITUS Research, and we have put together some blocks. And quickly we arrive at the limit, and the implementation fails because there is not enough available resources in the FPGA. So like we see here, if we put a DDC, an FFT, plus an FIR and a FFO, it is not possible in this platform. So we are strongly limited by the available resources. So some other limitation of the RFNOC usage is for each new design, you need to generate a new bit stream. And in this bit, the bit stream contains all the blocks we have previously chose. So we need to think before which block we want to use, because when we run the design, we cannot change block at one time. As we see before, we are limited by the FPGA available resources, and when we need to change from one configuration to another, we need to stop the design. So we arrived at the main contribution of our work. It is the question was, partial reconfiguration can be helpful to reduce or delete these shortcomings. So we will try to answer it. So what is partial reconfiguration? Partial reconfiguration is a modification of one or more portion of the FPGA logic while keeping the other portion of the FPGA in a running state. So we can have, we define a pair region, and we can modify the operation inside this region, and we keep all the other part of the FPGA in a running state. So we can have an operation running in the static part and was not stopped, and we can program a new functionality in the pair region and finally use it. So from a static design, we have now a dynamic design. So the advantage of the partial reconfiguration is to saving area and power by time multiplexing the hardware resources. So if one functionality is used only at one time and you want to replace it by another, this is possible. So also another advantage, it's reduce the configuration time with a partial bit stream compared to a full bit stream. But the partial reconfiguration comes with some limitation. So we cannot have in the pair region some the external I/O, the transceiver, the clock component, or external memory. We can only have programmable logic. Also, another limitation is the signal interface between the static part and the partial part cannot be changed at one time. So it is fixed before. And also the pair region, of course, it have a fixed size. So here in Xilinx, we call this a pay block. And of course, to apply the PR, we need it need extra step in the bitstream generation. So we have a partial reconfiguration on the SDR platform. So the partial reconfiguration could allow to swapping a block at runtime. So we can change block functionality. So we can have FFT and we can change it by FIR. We see that RF blocks have the same interfaces. So it is good with partial reconfiguration. And with the partial reconfiguration, you can have a full bit stream, one full bit stream. You load one time, and after you can reprogram only the pair region to change the functionality. And in the meantime, all the static part who is not affected by the pair region will be kept in a running state. So you can have a critical operation stay running during the partial loading. In our case, we have tested the pair region with E3 and 10 platform. So we can conclude that partial reconfiguration is a good candidate with RF block. Next step, to have this partial reconfiguration on the SDR platform, we need to add a freeze signal. Because during the loading process of the pair region, we can have some glitch on the interface between the static part and the pair part. So it will send some wrong data and we want to avoid it. That's why we had a freeze signal, and this freeze signal disables all the output of the pair block. This first signal could be controlled by the ARM processor. So when we want to program one pair region, we enable this symbol, write the pair bit stream, and after we can disable this signal and use a new functionality. So we have two methods to write the bit stream. We can use JTAG or through the processor with FPGA manager. So, but with JTAG, we need to open the SDR cases, like you see in the picture, and we need to connect a cable. And the programmation time is slow. It's more around a second. But with the deuxième option, through the processor, we don't need to open the SDR cases. We do not need to plug a cable. And the processing time is faster. It's more in range of milliseconds. So it's a good point. And the only thing you have to do is to enable the FPGA, the partial bitstream option in the FPGA driver. And this functionality is supported in UHD 3.14 and Linux 3.14.2 Xilinx version. But with the newest version of UHD, it uses a new FPGA driver, a new version, and this functionality is not yet supported. But it could arrive. We need to modify the driver. So to create a design, we should choose what we want to have in the pair region. So in the pair region, we put a RF node block, and the RF node could be a custom block or an RF node block from the UHD library. So we create the design with UHD image builder tools. Then we need to modify the design to apply the pair functionality. So we open it with Vivado and we do all the steps we need. We define a region in the FPGA, like we see here. And finally, at the end, we can generate the static bitstream and also the partial bitstream. We arrive to the test. So we define, first test, we define a custom RF node block, which a gain block. And we define a second one with a gain of 2. And we're testing it with a C++ program using the UHD API. So this program loads a static bitstream. After it can load a partial bitstream during watch time. It can stream data to the RF node block and collect the data and save it to a file. So we can see here the result. So we have first, after the static programmation, we collect the data with gain 1, and after we load the partial bitstream with gain 2, we can see the result as double, and here we can back again with static with partial bitstream of gain 1, and we see we have the same than at the beginning. So this validates the right functioning of the partial reconfiguration in a RF node block. Second, we can have a test with RF node block from UHD library. So I can show you with the demonstration. So here I am connected to the board where we see before. So here's the board connected with an Ethernet cable. And in the board we can first list, I have first program with a full bit stream. And we can list which block we have here. So here we can see we can have a radio, a DDC, FFT, and a FIFO. And we want to replace the FFT by the FIR block. So first we need to enable the option for partial bit stream. So it's there, and after we need to enable the freeze signal. So it's done, and after we can load a partial bit stream with FIR functionality. So here it's done, and after we need to disable the freeze signal, and we can list again the available block. And here we can see we have now a radio, a DDC, and an FIR, and the FIFO. So we can conclude it's working with the RFNOC block from UHD library. And we can, for the next slide, and we can also use a GNU Radio flow graph. So here we have tested. So after configuring the design, and you can change the block with partial bit stream. And after, yes, we want to use FFT. So here, as we can see, we can have a signal at the source, and we go to the RFNOC block, and we display it, and we can see you can have the FFT of the signal. So this validates the use of the GNU Radio flow graph with a partial bit stream. Last test, we have measured also the time elapsed to load the bit stream. So with a static bit stream, we have 143 milliseconds, and with a partial bit stream, we have 33 milliseconds. So a partial bit stream is 4 times faster than a static one. So it's a good step. So to conclude, FPGA partial reconfiguration is feasible in SDR devices. We can have a better use of FPGA resources by time sharing the hardware resources. So PR can be applied to a simple custom RFNOC blocks, or it could be also applied to a more complex RFNOC blocks coming from UHD library. And we have also tested the partial reconfiguration design with UHD utility, with a C++ program using UHD API. We have also tested with the GNU Radio flow graph, and all are validated. The future work, so pair is not mainstream yet. You need to do some part manually, and there is not available into the software of the currently available commercial SDR platform. So the objective of our work was to encourage the integration of partial reconfiguration support into the software of this platform. So if you want to have access to our work, you can look at our wiki, or you can have some information into the SDR Makerspace website, or you can contact us from the RAID Institute website. So thank you all, and I can answer to your question. Thank you.